In the scorched Arizona desert, among endless sands, lies the most expensive graveyard on the planet. 4,000 aircraft, worth over $35 billion. This isn't a museum and it's not a junkyard. This is where war machines that once ruled the skies come to die. Picture this: an area bigger than 2,000 football fields, and on every square foot, stories of wars, victories, and defeats. Legendary B-52s that bombed Vietnam rest here. F-14S that defended the skies over Iraq stand here. New patients arrive every single day. But what happens to these giants after they touch down for the last time? Some get stripped for parts in a matter of weeks. Others sleep here for decades, waiting for resurrection. And some just get wiped off the face of the earth. Stick around till the end. You'll find out how machines worth millions die and why this place is called America's Boneyard. (1946). World War II had just ended, and America faced a problem nobody had thought about. Tens of thousands of warplanes were suddenly obsolete. B-17Es, B-24Es, fighters, bombers, all worth billions, but the world wasn't at war anymore. Selling them was out of the question. The technology was classified. Keeping them on active bases? Too expensive. So the military found a solution: Davis-Monthan Air Force Base in Arizona, a place where it rains 4 times a year, where humidity is practically zero, and where the temperature kills any corrosion. Hard-packed alkaline soil, natural concrete, no need for hangars or runways. The desert climate turned this place into the perfect graveyard for aircraft. The first 600 planes from the war flew in. They were parked in neat rows, mothballed and forgotten. Nobody imagined that 70 years later, there'd be over 4,000 aircraft sitting here. The 60s, the Cold War is at its peak. America is building bombers capable of delivering nuclear weapons to Moscow. The B-52 Stratofortress. Weight, 83 tons. Wingspan, 184 feet. A machine built to destroy cities. By the 70s, they'd built over 700 of them. But technology changes fast. Missiles appear that fly faster and more accurately. Bombers become obsolete. Where do you put these giants? Davis-Monthan. The base is expanding. Now it's not just a storage yard, it's a whole industry. 365 personnel. Mechanics, engineers, preservation specialists. They take in aircraft, assess their condition, and decide the fate of each plane. Some get preserved for long-term storage. Others get stripped for parts within a month. Still others head to the Guillotine, a giant machine that slices the fuselage into pieces. The decision comes down to one thing. Does the military need this model? The Cold War is over, and at the airplane graveyard, the largest destruction in aviation history begins. The Strategic Arms Reduction Treaty demands proof. Bombers must be destroyed so Russian satellites can see it from orbit. They position a B-52 on the pad, and a 13-ton guillotine drops onto the fuselage. The crunch of metal echoes for half a mile. In 15 minutes, a machine that cost $100 million becomes chunks of aluminum. Cameras capture everything for the satellites, proof of destruction. Over several years, they cut up 365 B-52s this way. Each aircraft is a story. Vietnam, Operation Desert Storm, dozens of combat missions. But treaties matter more than history. The metal goes to the smelter. One bomber yields about 50 tons of aluminum, enough to make 1,200 bicycles. That's how legends of the sky die. process begins long before the aircraft touches down in Arizona. The military makes the call. This bird is retired. Could be a lot of reasons. Outdated model, maintenance costs through the roof, political decisions, structural wear after thousands of flight hours. The plane makes its final flight. Pilots joke it's the last ride to paradise, though for the machine it's more like a waiting hell. Davis-Monthan Base greets it in the receiving area. First thing, complete inspection. Engineers check every system: engines, avionics, hydraulics, electronics. A detailed report gets compiled. This will determine the aircraft's fate. Category 1. Storage with restoration potential. These birds can return to service in 5, 10, even 15 years. Category 2. An organ donor. Everything valuable gets stripped out. Category 3. My complete disposal. This plane goes under the cutting torch within weeks. Decision made. Preservation begins. If a plane ends up in storage, it's prepped for a long sleep in the desert. This isn't just park it and forget it. It's a meticulous process refined over decades. First, they drain all fluids: fuel, hydraulics, oils, every last drop. Even the slightest residue can cause corrosion or fire. Then they preserve the engines. They're coated with a special compound that protects the metal from oxidation. The cockpit is sealed. Every opening, air intakes, nozzles, hatches, gets covered with special film. It reflects sunlight and keeps the internal temperature from reaching critical levels. Without it, the cockpit turns into an oven. Desert temperatures in summer hit 120 degrees Fahrenheit. Electronics are sealed in protective bags with silica gel, which absorbs moisture. Landing gear gets treated with anti-corrosion coating. The whole process takes about 3 weeks. After that, the plane is rolled out to its spot. Neat rows like a parade of frozen giants. Here it can sit for years. But most aircraft meet a different fate. They become donors. Picture this: hundreds of planes flying overhead that need parts. An engine for an F-16 costs $3 million. Brand new. But what if you pull it from a mothballed airframe? $800,000. The savings are massive. That's why there's an entire disassembly industry here. Mechanics show up with orders. Need a radar? Pull it from tail number 412. Need a turbine? That F-15 over there will give up its own. The process is surgical. Aircraft aren't stripped barbarically. They're disassembled by the book. Every part gets cleaned, inspected, tested. They document serial numbers, flight hours, condition. Then they package it and ship it to warehouses. One retired aircraft can give life to dozens still flying. Every year, more than 20,000 parts ship out from here. The value of those parts? Over $500 million annually. The aircraft Boneyard operates like a giant parts store for all of American aviation. But some planes aren't so lucky. Their time is truly up. The model's obsolete and nobody needs their parts. Or treaties demand complete destruction. That's when the final act begins. The aircraft gets rolled onto a special pad. This is where the monster works, the Igor Guillotine. 13 tons heavy, tall as a 3-story building. It's a hydraulic cutter that can slice a B-52 fuselage clean in half in 20 seconds. Brutal process, but efficient. The blade drops and metal 3/4 of an inch thick cracks like cardboard. The fuselage splits apart. Then excavators with shears roll in. They cut the wings, rip off the tail, crush the cockpit. In one day, a single crew can turn 5 aircraft into a pile of scrap. Aluminum gets sorted by grade, titanium separate, steel separate. All of it goes to the smelter. One F-14 Tomcat yields about 12 tons of metal, enough to make 40,000 soda cans. Circle of materials. But not every plane stays here forever. Some come back to life. History's seen dozens of cases where an aircraft that slept 10 years in the desert took to the skies again. The most famous example? B-1 Lancers. In 2004, they were pulled from service and mothballed. 5 years later, the military realized they'd made a mistake. These machines were still needed. 18 airframes were brought back online. The restoration process took months. Engineers stripped protective coatings, checked every system, replaced all fluids, tested engines. Cost of restoration? $15 million per airframe? That's 10 times cheaper than building new. These B-1s flew combat missions again. Afghanistan, Syria, Iraq. Machines considered dead were dealing death once more. The Arizona desert proved to be better storage than any hangar. Dry air preserved the metal perfectly. Not a speck of rust after 10 years under open sky. $4,200 aircraft sit at the Boneyard today. That's more than all the aviation museums in the world combined. This collection's worth over $35 billion. Around 300 new birds arrive every year, and roughly the same number leave. Some for parts, some for the smelter, some return to active duty. The base operates year-round, 365 days. No days off. A staff of 400 keeps this giant machinery of death and resurrection running. The economic impact is massive. Annual savings for the U.S. Air Force, over $1 billion. Money they don't have to spend on new parts. Foreign militaries come here like it's a marketplace. They buy whole aircraft for their museums or training. Australia bought 20 retired F-18 Hornets. Israel took several dozen helicopters. The Boneyard's become an international hub for trading aviation history. And so, beneath the scorching Arizona sun, ends the life of machines that once embodied power and technology. Each of these aircraft isn't just metal and electronics. These are the stories of pilots who trusted them with their lives. These are missions flown over Vietnam, Iraq, Afghanistan. These are technologies humanity spent decades developing and billions of dollars perfecting. There's no museum romance here. Here's the harsh truth. Every machine is mortal, even those that ruled the sky. But there's a certain justice in this. Aircraft don't rot in junkyards. They donate their organs to brothers still flying. They transform into materials for new technologies. Some resurrect for final combat missions. The aircraft Boneyard isn't the end, it's transformation. From the ashes of old machines, new ones are born. And every time a fighter climbs into the sky with an engine stripped from a mothballed bird, somewhere in the desert a metal giant smirks. I'm still flying, just differently. What if the most dangerous part of a suspension bridge isn't what you see? Because inside the main cables, which look like solid metal, there's a structure made of tens of thousands of wires, each one vulnerable to destruction by even a drop of salty fog. So why doesn't a bridge weighing thousands of tons collapse every single day? And what happens if moisture gets inside the cable where nobody can see it? The Golden Gate Bridge in San Francisco has two main cables, each about 37 inches in diameter. Inside each one, 27,572 individual wires. If you unwound all these wires and connected them into one line, you'd get roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. The weight of just one of these cables? Around 24,500 tons. That's comparable to the mass of a small cruise ship. Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made of many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of kilometers. Stay till the end. You'll learn a secret that even bridge engineers don't talk about. Picture the classic example, San Francisco's Golden Gate Bridge. It's got two main cables draped over towers and anchored into massive concrete blocks in the rock. Each cable's about 37 inches across. That's not a cable anymore. It's practically a pillar you'd need 2 or 3 people to wrap their arms around. Inside, 27,572 individual wires, compressed into a perfectly round bundle. Unwind all those wires and link them end to end, and you've got roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. One cable weighs around 24,500 tons, comparable to a small cruise ship or several hundred fully loaded semis. Why so many wires instead of one giant solid rod? Steel handles tension beautifully, but it doesn't tolerate flaws well, especially in large cross-sections. When a cable is made up of thousands of individual wires, each one can give a little, taking on a bigger share of the load in some spots, a smaller share in others. If one wire happens to corrode or weaken for some reason, its contribution to the overall strength is minimal, and you won't even notice it in how the whole cable behaves. Plus, it's way easier to create a flexible shape out of tens of thousands of thin elements. A cable can smoothly wrap around towers, forming a big parabola across the span, whereas a solid rod of that diameter just can't be bent without permanent deformation. The process of making the main cables for a suspension bridge is nothing like how regular steel cables are made at a factory. Nobody ships a pre-made coil a yard thick and thousands of feet long to the construction site. A monster like that would be impossible to deliver or lift into position. So the main cables of suspension bridges are spun on site. It starts with installing temporary working cables between the towers. They run a traveling cart along them that can zip back and forth across the entire span. The cart carries a coil of steel wire. Each trip of the cart means threading another wire between the shores. One end of the wire gets fixed to an anchor on one side. The cart hauls the coil across the span. The wire gets secured on the other shore, and the excess gets cut off. Then the next wire, and so on, tens of thousands of times. To keep this insane marathon from turning into chaos, the wires get organized into what are called strands or subcables. For example, several hundred parallel wires get bundled into one strand of a specific diameter. First, all the wires get tensioned with a little slack. Then special jacks even out the tension so each little wire carries roughly the same load. Then the bundle gets clamped with rings or special bands to keep it from spreading apart. When there are enough of these bundles, they get brought together and compressed again into a single cylindrical structure. A spiral wrapping of thin round wire goes on top to hold the shape, plus a protective layer of paint or other anti-corrosion coating. At this stage, the cable can already hold incredible force. Picture a bridge deck suspended from it, a steel truss or box girder carrying the road surface. This deck structure transfers the load to the main cables through suspenders. Any vehicle crossing the bridge adds several tons to the system, sometimes dozens if we're talking about a semi or multiple trucks together. Wind pushes against the side of the structure with a force that can reach thousands of kilonewtons during a storm. Ultimately, the main cables feel all of this, stretching literally just a few inches along their entire length while staying within the elastic range. The beauty of a suspension bridge is that the cable works purely in tension, not bending or compression. That's the ideal mode for high-strength steel. The modulus of elasticity and tensile strength of these cables are specifically chosen so that working stresses stay well below ultimate limits, even accounting for wind gusts, temperature swings, and heavy traffic flow. During the design phase, engineers model every possible loading scenario. Both lanes completely filled with trucks, sudden braking, seismic events. The result? An acceptable range of cable elongation and sag within which the bridge remains safe and comfortable for users. Here's the fascinating part. Despite all that rigidity, the main cables aren't absolutely static. They breathe with the bridge. On a hot sunny day, the steel expands and the cables sag slightly. At night, as temperatures drop, tension increases and sag decreases. In windy weather, you might notice a gentle oscillation in the deck. The cables themselves are actually moving too, though it's invisible to the naked eye. It's precisely this living, flexible behavior that allows suspension bridges to handle dynamic loads better than rigid, overly stone-like structures. Excessive rigidity is exactly what led to disasters in bridge building history, while controlled flexibility allows the dissipation of vibrational energy. A separate critical topic: protecting cables from corrosion. Steel fears moisture and salty fog, especially in coastal regions like San Francisco. If water and aggressive contaminants get inside a cable, reaching each of the tens of thousands of individual wires, corrosion can silently eat away the cross-section for years until it's too late. That's why immediately after strand spinning and compacting are finished, cables get sealed. First thoroughly painted, then the coating is periodically refreshed. Modern bridges employ additional systems: wrapping with airtight tapes, filling gaps with dehumidified air or nitrogen, monitoring humidity inside. Regular inspections are conducted, including magnetic or ultrasonic non-destructive testing methods, which allow engineers to understand the condition of the wires without opening up the cable. All of this is done so that a single strand of infrastructure can safely serve for decades. The cables of the Golden Gate were designed for a service life of tens of years, but thanks to proper maintenance, regular repainting, and monitoring, they still do their job today, holding up the main span of over 4,000 feet. If you add in other suspension bridges around the world, the picture becomes even more impressive. Hundreds of thousands of miles of steel wire stretched across rivers, bays, and straits, keeping millions of cars suspended in the air every single day. Using main cables made from thousands of steel wires is standard practice for large suspension bridges, so the Golden Gate isn't alone here. One of its most famous relatives is the George Washington Bridge across the Hudson in New York. It also has two main cables woven from tens of thousands of steel wires. The total length of all that wire is measured in thousands of miles, and the mass of each cable runs into tens of thousands of tons, just like the Golden Gate. The same technology was used on the Brooklyn Bridge, though it's older and combines a suspension system with cable stays. There, the main cables also consist of a large number of thin wires, spun on-site rather than brought in as pre-made rope. Modern giants are built using the same principle. For example, Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made from many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of miles, and the design tension reaches hundreds of thousands of tons. A similar approach is used on numerous bridges in China and South Korea, which have been actively building long-span crossings over bays and wide rivers in recent decades. All these bridges share one technology: The main cables are spun on-site from tens of thousands of individual wires, each one tensioned, aligned, and compressed into a unified structure. This technology creates cables of incredible strength and flexibility, capable of holding thousands of tons and handling dynamic loads from wind, traffic, and temperature changes. And so, traveling from a coil of steel wire through tens of thousands of trolley trips across the void, through hydraulic jack tensioning and compression into bundles, through wrapping with protective wire and coating with anti-corrosion paint, the main cable of a suspension bridge is born, a structure of 27,572 individual wires, weighing 24,500 tons, able to stretch several inches under load but staying within elastic deformation, holding in the air a bridge over 4,000 feet long, carrying millions of vehicles every single day. Each wire is a separate element, and if one weakens, it's barely noticeable to the whole system. But if moisture and salt get inside, corrosion can silently destroy wires for years. That's exactly why modern bridges are equipped with humidity monitoring systems, regular inspections, and non-destructive testing. So these giants of steel and concrete can safely serve humanity for centuries.
Every year, the world produces billions of square feet of veneer, a petal-thin material hiding the strength and beauty of entire forests. Picture this. From a single log, you can get enough surface area to cover a football field. That's exactly why this industry is worth over $40 billion annually. From one perfect American walnut log, about 3 feet in diameter, you get anywhere from 10,000 to 30,000 square feet of unique surface. One log, almost an entire football field of veneer. Using veneer cuts the need to harvest valuable tree species by 98% compared to making furniture from solid wood. Instead of cutting down 20 trees to make 20 tables, you can harvest one perfect tree and leave the other 19 growing in the forest. But what's behind that number? How does an ordinary tree go through spa treatments, fiery tunnels, and encounters with scalpel-sharp blades to become luxury furniture? Watch closely. At the end, you'll discover a secret almost nobody realizes. Picture a lumber mill that specializes in veneer production. Massive logs of premium hardwoods, oak, ash, maple, walnut, cherry, arrive here by truck. But not every tree makes the cut. These have to be perfectly straight, tall trees with large trunk diameters, and most importantly, free of knots, cracks, and other defects for a significant height. Every knot is a scar that ruins the perfect grain pattern. That's why only the finest specimens are chosen for veneer. When one of these perfect logs arrives at the mill, it doesn't go straight to the blade. First, it gets the industrial spa treatment. The logs are submerged in enormous pools of hot water or placed in special chambers filled with hot steam. This isn't about cleanliness. This process, lasting anywhere from several hours to several days, at temperatures around 212 degrees Fahrenheit, does two crucial things. It softens the wood, making it more pliable and cooperative for cutting, and it transforms its color, making it richer and more uniform. After the hot bath, the bark gets stripped from the log. A special machine peels away the rough outer shell, revealing clean wood underneath. And now comes the most critical moment before the main show, centering. The log gets locked into the machine, and an operator uses lasers to find its perfect axis of rotation. This is absolutely crucial. Giant pencil in a giant sharpener. The log starts spinning around its axis, and the blade cuts into the spinning wood and starts shaving off a continuous wide ribbon of veneer, just 1/50th to 1/8 of an inch thick. It's like unrolling a paper towel roll. An endless, wet, flexible sheet comes out of the machine, which is then cut into pieces of the right size. This method is highly productive, but it creates a characteristic chaotic pattern that isn't always valued in high-end furniture. The second method, used to obtain the most beautiful decorative veneer, is called slicing. This isn't a sharpener anymore. It's the world's biggest cheese slicer. Here, a log, or part of it cut into beams, is firmly secured to a movable platform. Above it, or to the side, sits a massive, sharp blade. The platform with the wood moves back and forth, or up and down, and with each pass, the blade shaves off a single, perfectly flat sheet of veneer. It's a slower, less productive process, but it's what gives you that refined, linear, or figured grain pattern we value so much in expensive furniture. Depending on exactly how the log was cut before slicing, you can get different types of patterns: radial, tangential, mimicking the look of solid plank. Freshly cut veneer, no matter the method, is called green. It's soaking wet, flexible like damp paper, and tears easily. It needs to dry. The ribbons or sheets of veneer are carefully fed into a long drying chamber. Think of it as a giant tunnel oven, where the veneer slowly moves along on rollers or a mesh conveyor. Hot air circulates inside, gently and evenly pulling moisture out. The process is tightly controlled. Dry it too fast and the veneer will crack or buckle. Within minutes, that wet, floppy sheet becomes dry, slightly brittle but stable. After drying, the veneer sheets have ragged edges. They're stacked high and sent under a massive guillotine. A sharp blade slams down and in one stroke slices off the rough bits, creating perfectly straight edges. Now the sheets are ready for the most critical stage, where it's not machines doing the work, it's people with trained eyes. This is sorting. Specialists carefully inspect each sheet, evaluating its color, grain pattern, and any defects, then sort them into bundles by grade. It's meticulous work because this determines the veneer's price and application. But individual veneer sheets are often too narrow for making something like a tabletop, so they need to be joined into one large panel. This process is called stitching or splicing. Two sheets with perfectly straight edges are fed into a special machine. It presses them tightly together, and a specialized mechanism bonds them. This could be a thin zigzag line of adhesive or a glued paper tape. The result? A large, continuous veneer sheet, ready to be applied to a substrate. Now for some history. Using thin layers of wood goes back thousands of years. Ancient Egyptians used veneer to decorate sarcophagi and furniture 3,000 years ago. But modern industrial veneer production only began in the 19th century with the invention of steam engines and precision machinery. The first veneer peeling lathes appeared in the mid-19th century and revolutionized the furniture industry. Instead of sawing valuable wood species into thick boards and losing most of the material to sawdust, manufacturers could now obtain ultra-thin sheets, maximizing every inch of the log. The global veneer market is a massive industry, turning over more than $40 billion a year. The largest producers are China, the US, Germany, Italy, and Indonesia. Veneer isn't just for furniture. It's used in making doors, musical instruments, yacht interiors, luxury car interiors, and premium space finishes. But the most important application is plywood. Yes, ordinary plywood as we know it is multiple layers of veneer glued together with perpendicular grain direction. This exact structure gives plywood its strength and resistance to warping. And now the most impressive number behind veneer, its efficiency rating. Take one massive, perfectly straight log of premium American walnut, several yards long and about 3 feet across. If you just sawed it into boards, you could make, say, one big table and a few chairs. Now here's the kicker. If you slice that same log into veneer just 24 thousandths of an inch thick, you can get anywhere from 10,000 to 30,000 square feet of unique surface. To put that in perspective, that's enough to cover almost an entire football field from a single log. Using veneer cuts the need to harvest precious hardwoods by 98% compared to making solid wood furniture. Meaning instead of cutting down 20 trees to build 20 tables, we can harvest one perfect tree and leave the other 19 growing in the forest. This makes veneer one of the most environmentally responsible ways to use wood. But veneer has another hidden advantage that few people think about. The thing is, the most beautiful, unique wood grain patterns are often found in the most unusual parts of a tree, where the trunk branches out, in burls, in the root section. If you saw a tree like that into boards, these areas often end up as scrap because they're too small or irregularly shaped. But with veneer production, even a small section with a unique pattern can be turned into several square meters of luxurious material. There are entire categories of exclusive veneer made from burls, wood growths with incredibly complex, swirling patterns. One burl the size of a soccer ball can yield enough veneer to finish an entire study, and this veneer can cost thousands of dollars per square meter. There's even a market for archive veneer, material made from trees cut down decades or even centuries ago and stored in warehouses. Some species of wood that are now protected or extinct can only be found in the form of this archive veneer. Veneer manufacturing technology is constantly evolving. Modern machines are equipped with laser scanning systems that analyze the log structure before cutting and select the optimal angle and method to produce the most beautiful grain pattern. Computer control allows sheets less than half a millimeter thick to be sliced with precision down to hundredths of an inch. New processing methods are being developed that enable veneer to be stained, embossed with textures, and made to imitate rare species. And so, after journeying from a majestic tree in the forest through a hot bath at 200 degrees Fahrenheit, past a knife sharp as a scalpel, and through the fiery tunnel of a dryer, this material emerges, thin as a petal, carrying all the beauty, history, and unique character of the forest, ready to bring a piece of it into our homes. These billions of dollars aren't just money, they're proof that beauty and practicality can walk hand in hand, allowing us to enjoy nature's unique patterns without causing irreparable harm. Every sheet of veneer is a thin slice of a tree's history, one that lived for decades or centuries and is now ready to serve humanity for centuries more in the form of beautiful furniture.
Every hour, somewhere in the world, a metal component weighing over 50 tons is manufactured, and a single microscopic error in its machining can trigger a multi-million-dollar catastrophe. Picture a crankshaft as long as a bus that must survive a billion cycles of explosive force, or a cylinder block where a deviation the thickness of a human hair means scrapping a multi-ton giant entirely. But here's the mystery. How do engineers achieve micron-level precision when machining parts heavier than a tank? What happens in that secret quality control room where a computer measures thousands of points and can shut down the entire process? And most importantly, stick around until the end, because I'm going to show you the final operation where one tiny slip turns months of work into scrap metal. This is manufacturing where every thousandth of an inch is a matter of engine life and death. Ready to look inside? The first thing that hits you at this facility? the sheer scale. Forget your average car engine. Take this cylinder block, for example. It can weigh dozens of tons. This isn't just a casting, it's a complex, multi-layered masterpiece of foundry art, requiring special grades of steel or cast iron that can withstand unbelievable loads, temperatures, and pressures. And here's the crankshaft. In big engines, this thing can be as long as a small bus and weigh just as much. This component is probably the most critical. It has to endure the explosive force of fuel combustion, converting it into rotational motion. The blanks often arrive as massive forgings where every pound of metal already has its own story. The process starts with incoming inspection. Specialists check the chemical composition, scan for internal defects using ultrasound and X-ray equipment. Because even the tiniest hidden flaw in a part this massive could lead to catastrophe during operation. It's like a health checkup for a steel giant. Only after a thorough inspection does the blank get clearance to enter the machine shop. Moving these blanks takes serious muscle. That's why the shop is equipped with powerful overhead cranes capable of lifting loads that outweigh most ordinary machine tools. Mounting the part onto the machining center is a precision operation requiring coordination and experience. This is the first step in turning metal into might. Now we move to the heart of the shop, the cylinder block machining zone. This is where multi-axis machining reigns supreme. Before you stands a gantry-type milling machining center. It looks more like a small house than a machine tool. Its spindles, fitted with ultra-hard cutting inserts, can remove up to several hundred pounds of metal per hour. The first operation is roughing. The goal, remove excess stock, eliminate surface casting defects, and give the part its basic geometry. The speed and sheer aggression of this cutting process? Absolutely mind-blowing. Those streams of hot chips tell you everything you need to know about the energy being dumped into this transformation. But the real magic happens later, during finishing operations. Remember when we talked about precision? For diesel engines, perfect cylinder geometry isn't just important, it's critical. That's where boring and honing come in. Boring creates the cylinder holes with micron-level accuracy. The slightest geometric error means uneven wear, compression loss, and ultimately engine failure. And honing, that's the final touch. A specialized tool with abrasive stones creates a micro-texture on the cylinder's inner surface, what we call crosshatch. This crosshatch is essential for holding oil and ensuring perfect lubrication of the piston rings. We're talking about polishing at nearly molecular level, guaranteeing engine life measured in decades. These machines operate under strict temperature control. Any temperature fluctuation can cause thermal deformation in a part weighing several tons, which means losing precision. That's why the shop floor maintains a constant microclimate, and the machining itself can run for days. Up next, meet our next hero, the crankshaft. This component works under the most demanding conditions. It needs not only colossal strength, but perfect balance. Manufacturing it, an engineering masterpiece. First up, preliminary journal machining. On specialized CNC turning milling machines, the connecting rod journals and main journals take shape. Given the weight and length of the shaft, unique support systems are used here to prevent sagging and vibration during machining. The critical stage, grinding. The shaft journals must have minimal surface roughness because that's exactly where friction with the bearings occurs. The smoother the surface, the less friction, and the longer the engine lasts. Special cylindrical grinding machines with highly sensitive sensors handle this job. Now, for the critical part, heat treatment and surface hardening. After grinding, the crankshaft journals undergo induction hardening or nitriding. What does this do? It creates a super hard, wear-resistant layer on the journal surface while maintaining the core's toughness and strength. This is essential so the shaft can withstand billions of load cycles. Think of it as armor for the engine's most vital component. Final stage, balancing. Given the massive weight, even a tiny imbalance can destroy the engine. That's why every crankshaft goes through dynamic balancing. If the machine detects a deviation, counterweights are added, or material is removed from the flywheel sections until the shaft achieves perfect balance. It's like tuning a violin, except instead of music, we get harmony of rotation and power. How do you achieve that kind of precision when working with such giants? The answer lies in the tooling and quality control. The tool itself is a high-tech product. Every cutter, every mill is equipped with carbide inserts or even synthetic diamonds. They have to withstand enormous temperatures and cutting pressures. Special coatings extend the life of these tools while keeping machining quality consistently high. In a dedicated tool room, there's constant monitoring of their condition, resharpening, and replacement. But the most important thing is quality control. After every key operation, the part undergoes rigorous measurement. Coordinate measuring machines help us with this. These machines, equipped with high-precision probes and laser scanners, can measure up to 1,000 points on a part's surface with accuracy down to a few micrometers. They create a three-dimensional map of the part and compare it to the perfect computer model. If the error exceeds the tolerance, the process stops, and the part gets sent back for rework or, worst case, scrapped. No part leaves the shop floor until the computer gives the green light on its perfect accuracy. And then, when all the components, the block, crankshaft, cylinder heads, connecting rods, have passed strict inspection and achieved perfect precision, they're ready for the final stage. Assembly. This is a different shop, where sterile cleanliness reigns. Assembling an engine like this is no less precise a process than machining. All parts are thoroughly washed, removing even microscopic traces of metal chips and dirt. Specialists use torque wrenches to tighten thousands of bolts to a precisely defined spec. A mistake in torquing the cylinder head, for example, can lead to a blown gasket and engine failure. Every stage of assembly is tracked and controlled by electronic systems. Not a single bolt gets tightened without computer confirmation. After assembly, the engine heads to the test stand. Here it's fired up and gradually brought to operating conditions. Sensors measure temperature, oil pressure, vibration, power output. Any deviation from the norm, and the engine goes back for rework. Only after successfully passing all tests does the engine receive its quality certificate. These giants get installed on ocean vessels, locomotives, mining dump trucks, power plants. One of these engines can run for decades, churning out thousands of horsepower. And behind every hour of its flawless operation stand months of work by engineers, machine operators, quality inspectors. Manufacturing these engines is the pinnacle of mechanical engineering, where metallurgy, precision mechanics, and computer technology converge. And just like that, starting from a multi-ton forging, through rough and finish machining, through honing with precision down to microns, through heat treatment and balancing, through sterile assembly and rigorous testing, an engine is born, capable of running billions of cycles without a single failure. This is the story of how humanity learned to create steel hearts for the most powerful machines on the planet. Every crankshaft, every cylinder block, it's a symphony of engineering thought where an error of 1 micron means failure, and success means decades of flawless operation. When you see a massive ship crossing the ocean, or a locomotive pulling thousands of tons of cargo, remember, at its heart beats an engine, every part of which has passed through the hands of master craftsmen and the scrutiny of computers. This isn't just metal, it's the embodiment of humanity's drive for perfection, where precision is measured in microns and reliability in decades of impeccable service. Picture this. Glass that once shattered into deadly shards now saves lives. How did humanity transform a fragile substance into armor for your car? Every year, the world produces over 100 million square meters of automotive glass, enough to cover an entire country. But the real magic happens where molten rock becomes a perfectly smooth surface, in furnaces reaching temperatures over 2,700 degrees Fahrenheit. That's hotter than the surface of molten lava. How did ordinary quartz sand become the foundation of a safety technology we can't imagine modern transportation without? What accidental experiment changed the history of automobiles forever? You'll discover how the first safety glass was created, what secrets hide within its layers, and why modern windshields can withstand the impact of a rock at 60 miles per hour. Watch until the end. The finale reveals how many stages glass goes through to protect your life. The history of automotive glass production is closely tied to the development of the automobile industry, which emerged in the late 19th century. When the first cars began appearing on roads, they weren't equipped with glass at all. The open body design only partially protected passengers, while dust, wind, insects, and other hazards made trips extremely uncomfortable. Later, as cars got faster, the need arose to install protection for drivers and passengers. Windshields started being made from ordinary window glass, which, while providing some protection, had a serious flaw. During accidents, it shattered into large, sharp shards, leading to numerous injuries and deaths. Glass sliced faces, necks, arms of drivers and passengers. This was a real problem demanding an urgent solution. The first revolutionary breakthrough in automotive glass came with the creation of laminated glass, and it happened by accident. In 1903, French chemist Edouard Benedictus accidentally knocked over a flask coated with nitrocellulose. The glass cracked, but stayed intact thanks to a thin plastic layer. This accident inspired the scientists to create multi-layer glass, which later became the foundation for laminated safety glass. By the 1910s, laminated glass started appearing in premium automobiles. Its construction consisted of 2 glass layers with a thin, transparent film sandwiched between them. On impact, the glass wouldn't shatter. Cracks would stay trapped in the film. In the 1920s, laminated glass became widely used in windshield production. Its main advantage? Enhanced safety. Even in serious crashes, fragments wouldn't fly everywhere. They'd stay locked in the polymer layer. The next stage in automotive glass development came in the 30s, when tempered glass manufacturing technology was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it shattered, it broke into small pieces with blunt edges, minimizing injuries. In the mid-20th century, tempered glass began to be used for side and rear car windows. It was cheaper to produce compared to laminated glass and provided a sufficient level of safety for these parts of the vehicle. In the 50s and 60s, automotive glass became even more advanced thanks to technological developments. Important changes occurred. Improvements to laminated glass and the development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production and automation of manufacturing processes allowed for a reduction in the cost of automotive glass. One of the biggest technological breakthroughs in glassmaking came in 1959 with the invention of the float process. This technology, developed by British company Pilkington, made it possible to manufacture perfectly smooth glass by spreading molten glass across a surface of molten tin. Picture this. Red-hot liquid glass pours onto a mirror-like surface of molten metal and spreads itself out, forming a perfectly flat sheet. Thanks to this method, glass became more uniform, stronger, and accessible for mass production. The float process is still the foundation of automotive glass manufacturing today, ensuring precise dimensions, smooth surfaces, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 60s, heating wires started being installed in rear windows to prevent fogging and freezing. In the 80s, glass with special metallic coatings appeared that reflected sunlight and reduced cabin heating. UV protective glass, thanks to new technologies, began providing nearly complete protection from harmful radiation. Modern automotive glass is divided into several types depending on its purpose and manufacturing technology. The windshield is typically laminated glass consisting of 2 layers of glass with a polymer film sandwiched between them. This design ensures that when damaged, the glass doesn't shatter into sharp fragments. Side and rear glass are most often tempered glass, which breaks into small blunt pieces upon impact, reducing injury risk. Panoramic roofs or other specialty glass types often use laminated or tempered glass with special coatings for ultraviolet radiation protection. The main components of glass are natural materials mixed in specific proportions to achieve the desired properties. Quartz sand is the primary ingredient of glass, providing its transparency. It must be extremely pure with minimal impurities. Soda is added to lower the melting point of glass. Lime improves the mechanical strength and chemical properties of glass. Additional additives are used to adjust color, transparency, resistance to ultraviolet light, and other characteristics. The raw materials are purified, dried, and ground to a uniform consistency. It's critical that impurities that could affect glass quality are eliminated as much as possible. After the raw materials are prepared, they're loaded into specialized furnaces for melting. The melting temperature to form glass reaches around 5,000 degrees Fahrenheit. This is the temperature at which stone transforms into liquid. During the melting process, the raw materials become a uniform, viscous fluid. The glass mixture gets stirred to distribute components evenly. This matters. You want to avoid air bubbles or inconsistencies in the finished product. Glass melting furnaces come equipped with modern temperature control systems and process automation, ensuring top quality end results. After melting, the glass mass undergoes forming, which in modern production is most often done using the float process. Liquid glass flows out of the furnace and enters a bath of molten tin. Thanks to tin's high density, the glass mass spreads evenly across its surface. Under its own weight, the glass forms a perfectly flat and smooth surface. Gradually lowering the temperature, the glass hardens. By the time it exits the bath, it's ready for processing. The float method allows manufacturers to produce glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions needed for automotive production. Automated cutting machines ensure precision in the process. To prevent cracks and chips, the glass edges are ground down. Each sheet undergoes inspection for defects like microcracks, bubbles, or other damage. To guarantee the strength and safety of automotive glass, it goes through a tempering process. The glass is heated to around 1,112 degrees Fahrenheit. Then the glass surface is rapidly cooled by air jets, while the inner layers cool more slowly. This creates tension that increases impact resistance. When tempered glass breaks, it shatters into small, safe fragments, minimizing the risk of injury. Windshields use laminated glass, a construction of glass and polymer film. Its manufacturing involves several steps. A polymer film is placed between 2 glass sheets. The construction is put into a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure. This creates a rock-solid bond between the layers. Laminated glass has exceptional impact resistance, and when damaged, it stays held together by the polymer film, keeping drivers and passengers safe. To enhance automotive glass properties, various coatings are applied. Anti-glare coatings reduce reflections from the sun or headlights of other cars. UV protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings make water sheet right off the glass surface. Heating elements. Thin heating wires can be embedded in the windshield, making it easier to clear ice or fog. To achieve the exact shape needed, special thermoforming equipment is used. The glass is heated to a temperature where it becomes pliable and is formed according to the specified parameters. In the final stage, every piece undergoes rigorous inspection. They check for clarity and defects. The glass is tested for impact resistance and load endurance. Standards compliance, dimensional accuracy, shape, and other parameters are verified. The finished automotive glass is packaged to prevent damage during transport. It's shipped to auto plants or service centers where it's installed in vehicles. And that's how, journeying from quartz sand through the hellish flames of furnaces at 5,000 degrees Fahrenheit, through a bath of molten tin, through tempering and lamination, glass is born, capable of protecting life at 75 miles per hour. This is the story of how an accidentally shattered flask changed the automotive world forever. Automotive glass production is a high-tech process combining physics, chemistry, and engineering. Thanks to modern technology and strict quality control standards, automotive glass delivers safety, comfort, and durability. Every time you get in a car, remember, between you and danger, a thin layer of glass that's passed through dozens of production stages to save your life in that critical moment.